Okay, well, real quickly, should only take a moment here. We're going to be solving question 8. What is the gravitational force between two 15-kilogram balls whose centers are 35 meters apart? And then what fraction of this is the mass, or the weight, actually, of one ball? All right, so what's our equation? It is the force, gravitational force between two objects is the universal gravitational constant multiplied by the product of the two masses, mass 1 and mass 2, divided by the square of their radius. So in our case, we're going to have, I don't know if I can do this. Let's see. Nope, I can't. Okay. So we're going to have to go get the universal gravitational constant, which is 6.67. We'll just call it 6.67 times 10 to the negative 11th. All right. So 6.67 times 10 to the negative 11th times M1 are both 15 kilograms, right? 15 times 15 divided by the square of the distance between them, right? And they are 35 meters apart. We don't have to worry about the units because everything's in base units, kilograms and meters. 35 meters apart, and that has to be squared, right? So now we'll just do that. We'll just start with, let's start with that fraction. And that fraction is going to be 15 times 15 on the top divided by 35 squared on the bottom. So that is going to give us, so that's going to be, I'm just going to put G in here. We know G is 6.67 times 10 to the negative 11th. So that's G, but that's the worst G ever, isn't it? There. Now it's a G. It's still not a G, but whatever. Times, and what do we get here? We got 0.01367. I should be looking at the screen when I do that. Okay, so that's going to be 1.367 times what? 10 to the negative 1, 2 times 10 to the negative 2. So we're multiplying powers of 10, 10 to the negative 11th times 10 to the negative 2. So that's going to be 10 to the negative 13. And then we're going to have to go 6.67. 6.67. Let's see. Times 1.367. And that's going to give us 9.12. 9.12 times 10 to the negative 13th newtons is the force of gravity between two 35 kilogram balls whose centers are 35 meters apart. And that's what we would expect, because if you pick up two things that weigh 15 kilograms, you do not sense the force of gravity between them. So that's it. And in terms of what fraction that is of the weight of one ball, well, it's a little confusing that they said weight, but that is the force. They're both pulling on each other with the same force. So when it says what fraction of the force it is, it's 100% of that force. Okay. Number 10, gravity. If Earth began to shrink, but its mass remained the same, what would happen to the value of G on Earth's surface? Remember, little g is the force of gravity, right? The big G is the universal gravitational constant. So let's go back to this equation for number 10. And if so this is basically equivalent to a little g, because that's the force of gravity, right? So if Earth began to shrink, but its mass remained the same, so what are we talking about is happening there? We're talking about this, the bottom of the fraction going down in the minus direction, while the top of the fraction holds steady. So what's going to happen? Well, if the bottom of the fraction gets smaller, then the whole thing gets bigger, right? So G would be increasing. In the case of this is again, I did not say in the beginning, this is number 10. In the case of number 10, if Earth began to shrink, but its mass remained the same, the value of G, the force of gravity on the Earth's surface, would increase because the radius is getting smaller. That's all. Bye-bye.